All right, so this is the second edition of some reaction videos to awesome physics teachers doing problems. Today I just did a Google search for homework 6 physics. Just made up the number 6 just to see what I could find, and boom, here we go. So let's get started. Actually, I'm going to make it double speed before we get going. You can always do this in YouTube. And ready.
Hello, AP Physics 1 students. This is Mrs. Drost, and today we're going to be working on homework 6, projectile motion, question number 4. So what do we got? We got a ball that is kicked, and it travels 30 meters above the ground and 45 meters forward.
Boy, oh man, I love how excited she is. I love how, it's just like, man, you guys, we have to build these muscles. Let's do this problem. Very awesome.
Horizontally, what is the initial speed of the ball and the angle that it was kicked? All right, first thing I always do, draw myself a picture. Okay, so I got a ball. Okay, it's kicked, it's on the ground, so it will follow a projectile path, a nice parabola. My picture isn't so beautiful. Okay, I know, what do I know? I know horizontally I traveled, actually, let me write this. This is my delta x. And it's
Oh, that was super cool. First of all, the drawing, fantastic. When she drew the ball up here, I was like, what's she doing? But she had enough room just to fit that in. That was super awesome. And then she was going to say this was 45 meters, but then she's like, actually, hang on, let's call it a variable. Let's call it delta x. I love that.
equal to 45 meters. Okay, and then I also know my delta y.
Ooh, colors.
Not a very good picture here. Okay, here we go. Delta y. That's how high it was above the ground, and that is 30 meters. And what do I want to know? I want to know the angle that it was kicked at, I don't know, and how fast was it going.
Oh, I love that. I love how she drew the angle to be tangent to the curve, right? I mean, my guess is already in this class, hey, this is problem number 4 already of homework number 6. The idea that, right here, the angle's there. She didn't, draw it along the curve, which I think a lot of students would do. I think her purple little line here probably only goes to the blue line, it turns out. But of course, she knows that she wants it to go to the vector. So that was very cool.
So it doesn't look like I'm given a whole lot of stuff. But what other things do I know? I know my acceleration is equal to negative 9.8 meters per second squared, because we can say this ball is on Earth. I know the velocity, the initial velocity of the ball.
This ball was on Earth.
I don't know the initial velocity of the ball. I know the velocity in the y direction at the peak is equal to 0. So I know it's going, at the very peak, at the top of its arc, my y velocity is 0. My x velocity is always the same. Okay,
Whoa,
so.
Some super awesome stuff in there. She's like, oh, it's on Earth, so we know that, and we know what's happening at the peak. So just really driving home some basic ideas for her students to be able to use. Some very straightforward things. It doesn't say the Earth on here, but, what a great way to, for example, make adjustments to this problem later, what happens on the moon, that kind of stuff. But yeah, this is just a subtle reaffirmation of what happens at the peak of the trajectory here about, this, and that the x velocity always stays the same. Very cool.
Oh, I don't know how long it's in the air, so I don't know what t is. All right, so it doesn't look like we have a whole lot of stuff when we get started, but let's see what we can do. I do know, one other thing I do need to know, if I want to know this initial velocity and this angle, how do I find that? Okay, if I want to know this and this angle, I need to know my initial velocity in the x direction and the initial velocity in the y direction.
Love it.
Then I can use vector math to find out what this is. Okay, so this is my goal. My goal is to find the x velocity and the initial y velocity so I can calculate this angle and this speed. Okay, so that is where I'm headed.
Ooh, erasing.
All right, so let's see what I got.
So erasing is such an interesting feature, right? So it really sort of drives the students that they have to watch the video, because the the product at the end is maybe not even going to be understandable. And of course, for me, asking students to do this kind of video work, I've found it to be super, super useful to just listen to them. And it's okay if they erase, as long as they tell me what they're up to. Very cool.
Horizontally. Okay, next thing I always do is I look at, what do I have horizontally, what do I have vertically? And again, horizontal, Vx is equal to delta x over t. I don't know what Vx is. I need it, but I don't know what it is. I don't know what t is, but I do know that my horizontal distance is 45 meters. All right, so at this point, I can't go any further with my horizontal stuff. So
I love that she makes it clear, I can't go any further, right? So there was this very straightforward formula, which I guess she erased right before I hit pause. And she's like, well, good Lord, if it were this easy, we'd be done. But obviously, we have to do some more work.
Now I'm going to look and see, what can I figure out vertically? Okay, vertical.
Colors. Oh, this is OneNote.
I know.
I love using OneNote.
A is equal to negative 9.8. I know delta y at the peak is equal to 30 meters. I know my velocity at the peak is equal to 0. Oh, this is looking promising. And what do I want to know? Well, I want to know my initial velocity in the y direction, because that will get me my vectors that I need. And I also want to know what the time is, because the time I can plug into here to find this x velocity. Okay, so, awesome. But I think I have enough information with this to say delta y, oh, I'm sorry, v squared at the peak is equal to v naught squared plus 2a delta y. Yes, okay, so my velocity is 0.
So it's really interesting, right? So this formula is really an energy formula. So this is basically kinetic energy, and this is basically work. And so it's not presented that way to students. Usually it's derived through a fair amount of algebra to get to this. But it's so useful. And what I love about it is that when you then do get to energy, just sort of multiply by 1/2 m, and you're like, oh, we've been using this all along. So that's actually really a cool way to sort of drive home the energy concept, even though they might not have even used the word energy yet at this point in their classes. I mean, I don't know, but this formula is such a useful formula, and students use it all the time for problems like this. And of course, it turns out it's just an energy formula. And so I just love how you sort of plant that seed in the students.
I'll call this. I don't know what my initial velocity is in the y direction, but that's what I'm trying to figure out. Plus 2 times negative 9.8 times 30. So if I plug that in to my calculator, I end up with what? 2 times 9.8 times 30 is equal to this. All right, I get 24.25 meters per second.
I love how she just grabs her calculator right then and there.
Okay, 1 part.
And I love that the significant figures don't matter at all. Love it.
I want to know what v is. I want to know what theta is. So I need to know the x, and I need to know v naught y. All right.
The idea of redrawing something that she had used before. Of course, it's a savings of space, but now she's using colors, which is super cool. She's being super consistent with her color use. Oh, that's so awesome. And to redraw, really, if you had it drawn on the page, you had enough room, I suppose you could go back and point to it again. But to redraw it really drives home again what's going on. Man, it's super cool.
All right, I figured out v naught y, so that's a good thing. So I've got this part figured out. All right, I still need to figure out this part, the vx. But in order to do that, I need the time. Where can I get that from? I can get that from the vertical information. Okay, so let's see, how can I figure this out using the time? Okay, I can do it 2 ways. I can say delta y is equal to v naught y t plus 1/2 at squared. Or I can say delta y is equal to 1/2 v naught y, or v plus v naught times t. And either one will work. Either one will get you the right answer. This one is a quadratic. This one looks kind of messy, so I'm not going to use this one. Okay, so let's use this one. But I'm going to rewrite it in a better spot. Okay, and the other piece of information, when I use this equation, delta y is equal to 1/2 v naught y plus v at the peak times t. That gives me how much time it takes me to get to the peak.
Again, super cool, right? So in so many of these problems, the way that things are changing is quite linear, and so that's why you can do this averaging stuff. And it was really interesting. She's like, oh, we could do this quadratic thing. Ugh, who wants to do a quadratic thing? Let's do this. And so, really driving home that either way it's going to work is very cool.
Okay, and then I have to double that time to get it for the whole trip, because for the amount of time it takes you to go up, it takes you the same amount of time to come back down. So remember, when we use this equation, this is half of the total time. Okay, that's another piece that you just kind of have to remember. So let's plug this in. We get 30 is equal to 1/2 times 24.25. My velocity at the peak is 0 times t. T, when I do this, is equal to, let's see, 30. Wait. Sorry, 24.25.
0.125.
Divided by 2.
Oh, that's just that.
Times 30. All right, I get 2.474. Let's just do 2.474 seconds.
Oh, I love it. I love this mix-up of significant figures.
And so what is my total time?
Man,
if I multiply that by 2, my total time is going to be equal to, let's multiply that by 2, 4.95 seconds.
All right. So 5 seconds to go 30 meters.
So now, all right, now I know my time. So I'm going to take...
Oh, this is really high. Okay, yeah.
Now I've got all that figured out. I know that my initial velocity, I'm going to erase this for some space. But what have I figured out? I have figured out this one is 24.25 meters per second.
Ooh.
I figured out my time is equal to 4.95 seconds.
She had the space, so you filled it in. Super cool. Oh, I love this too.
Vertically for 4.95 seconds. It's in the air horizontally for 4.95 seconds. Okay, so now the next step that we have, I have now figured out, I have enough information now to figure out what my horizontal velocity is. So now I'm going to use this equation. Vx is equal to delta x over t, and I can find my horizontal velocity. Okay, Vx, my delta x is equal to 45, my time is equal to 4.95. So now my horizontal velocity, which is a constant velocity, is going to be equal to
8, 9, something.
9.09 meters per second.
Okay, that's pretty fast.
So guess what, guys? We are very close to having, well, actually, now we know the components of our vectors. Okay, so now we can figure out our total velocity and the angle that it was launched at.
So just to point out, right? So imagine this was the final product, and the students just had this. It wouldn't make any sense. The video really walks you through. The colors are helpful, but really talking through what's happening. What a difference a video solution versus a written solution. A written solution would have taken up way more space, and of course you would have had to write a whole lot more. But I'm in. I really love this.
Fortunately, I'm out of space, so I'm going to erase some stuff here. Hold on. so I can finish off this problem. Okay.
Looks like OneNote erasing.
Takes a little longer to erase than you think. All right. I got a nice clean workspace almost ready. Okay, I'm going to redraw my picture. This is where this vectors that we did first unit comes in really handy. I'm going to redraw my picture. Okay, what do I want to know? I want to know V.
Oh,
okay,
redrawing again.
So I want to know the initial speed, the total initial speed, and the launch angle. Okay, I do know that this component, Vx, is equal to 9.09. And I know the vertical component, the initial velocity vertically, is equal to 24.25.
Oh, she had that erased.
All right,
She must
so
have found that somewhere else.
Okay. The
Oh, no, it's right there.
there's multiple ways.
That's right
Tangent
here.
theta is going to be equal to sine over cosine, which is 24, or the opposite over the adjacent, which is 24.25 divided by 9.09. Okay, and then if you plug that into your calculator.
Okay, let's just pause. I love the fact that here's a trigonometric function that puts sine on top. Oh, yeah.
Use the inverse tangent or the arctangent function, you get 24.25 divided by 9.09 is equal to 2.67, inverse tangent. All right, I get 69.5 degrees.
Whoa!
And that's north of east. Because it's going up and to the right.
So,
Okay, so I know my launch angle.
oh, wow. Wow, that's north of east. That's fascinating. Right, so she's using on the piece of paper, she's describing north to be up and east to be to the right. But the person didn't kick it north of east. Oh, so interesting to be able to multiple use of such an interesting representation. That must be fun to talk about in class, because I could imagine some snarky student just saying, well, I didn't kick it that way, I was kicking it south. Wow, that's super interesting. Wow, this appears to be done. I'm going to just see how she wraps it up here.
How do I know how fast it's going? I'm going to use the Pythagorean theorem. V is going to be equal to the square root of 9.09 squared.
Oh, right.
Plus 24.25 squared. So if I plug that into my
It's going to
calculator.
be 26.
Plus 24.25.
27. 30. 28.
I get my initial speed is about 25.9.
Just stuck to my guns.
Whew. So that is how you solve problem 4. Hope that.
Oh, I love that. Woo! That was really great. Good job. Good job. Love it.